This glitch in a 1996 video game let kids duplicate rare items. This bug in 2014 exposed the encryption keys for most of the internet. This vulnerability from last month is in the phone in your pocket. Same bug, 50 years apart, still shipping. This is the story of why memory management is the hardest problem in computing, and why every new language for the last 20 years has been trying to solve it. And here's why this matters right now. Every AI model you've deployed this year, every LLM, every inference engine runs on infrastructure written in C. CUDA is C. The Linux kernel is C. The entire AI stack sits on top of memory-unsafe foundations. The bug you're about to see isn't history. It's the floor your models are standing on. Before we get to the bugs, we have to understand the model, because the bug isn't in the code. It's in the model the code inherits. In every modern computer, memory is a single flat array. Addresses run from 0 to however many bytes of RAM you have. Your variables, your passwords, your encryption keys, the instructions currently being executed. All of it sits in the same array, next to each other, with nothing between them. That's it. That's the entire problem space. Every memory bug we're about to look at is a variation on one question. What happens when code writes past the boundary of where it's supposed to, into memory that belongs to something else? C, the language that most of the world's critical infrastructure is written in, does not check this. You asked for a 64-byte buffer. C gives you a 64-byte buffer. If you write 128 bytes, C writes 128 bytes. The extra 64 go into whatever lives next door. This isn't a bug in C. This is C's design philosophy. The programmer is responsible. The language gets out of the way. That philosophy was correct in 1972. It has been catastrophic ever since. The earliest buffer overflow most engineers ever encountered, even if they didn't know it, was in a Game Boy cartridge. In Pokémon Red, when you talk to this NPC, the game stores your name in a temporary buffer used for his tutorial battle. The buffer is never cleared. When you later surf along Cinnabar's east coast, a zone with no defined wild Pokémon table, the game reads that same memory region to decide what wild Pokémon appears. The encounter table is your name. The bytes of your name become Pokémon IDs. Missingno isn't a glitch Pokémon. Missingno is you. This is a read overflow. The code read memory it was supposed to have no knowledge of. The consequences were cosmetic. Duplicated items. Corrupted save files. But the architectural flaw is the same one we'll see at nation-state scale in 2 minutes. 8 years before Missingno, a 23-year-old grad student at Cornell released a program that infected roughly 10% of the machines on the early internet. One of its propagation methods, a stack buffer overflow in the Unix fingered daemon. This single C function reads input from the network and writes it to a fixed size buffer. It does not check the input's length. It has been deprecated since 1999 and removed from the C standard in 2011, and it is still responsible for active vulnerabilities in legacy systems today. Morris wrote a payload longer than the buffer. The overflow wrote past the end into the function's return address. When the function returned, the CPU jumped to Morris's code instead of the caller. Remote code execution. 3 years probation, 400 hours community service, and the first computer fraud conviction in U.S. history. The bug was architectural. The punishment was personal. 13 years later, Microsoft IIS, the web server powering hundreds of thousands of production systems, has a buffer overflow in its URL parsing code. A worm called Code Red exploits it. In 14 hours, 359,000 servers are infected. The worm defaces websites, attempts to DDoS the White House, and costs an estimated $2.6 billion. Same bug, same pattern, different decade, different victim. Which brings us to 2014, and the bug that more than any other forced the industry to confront what C actually costs us. OpenSSL, the library that handles TLS for roughly 2/3 of the web. Banks, email providers, VPNs, government infrastructure. Before Heartbleed, it was maintained by essentially 2 people, part-time, funded by donations of about $2,000 a year. 2 people, $2,000, protecting trillions of dollars of commerce. This is not a charming story. This is a systemic failure in how we fund critical infrastructure, and it has not been fixed. Now the code itself. This is the TLS Heartbeat extension, a small feature that lets 2 endpoints confirm they're still connected. One side sends a payload with a claimed length. The other side echoes it back. Notice what this code does not do. It does not check that the claim length of the payload matches the actual length of the payload. A malicious client can send a 1-byte payload and claim it's 64 kilobytes. The server dutifully copies 64 kilobytes out of its own memory into the response, starting at the 1-byte payload and continuing into whatever happened to be adjacent in the heap. Session keys, private keys, authentication tokens, user passwords, whatever was there. Today, an AI scanning this code can flag the missing bounds check-in under a second. In 2011, a human reviewer missed it on New Year's Eve. But here's the part no one wants to say out loud. The same AI that helps defenders audit code also helps attackers find exploits at machine speed. Every unfixed buffer overflow in every legacy C code base is now searchable, automatically, at scale. The analogy that finally made this click for me. A library patron asked for the book titled Cat, which, they claim, is 64,000 pages long. The librarian does not verify. She hands over Cat and 63,999 pages of whatever was next to it on the shelf. Private correspondence, medical records, financial statements. That is Heartbleed, executed against the entire internet, silently, for 2 years, with no log trace. The fix was one line: check the length. That is the entire correction. The code that introduced the bug was committed on New Year's Eve 2011. It was disclosed in April 2014 for 836 days. Anyone who knew about this bug could read the secrets of most of the internet. We do not know who knew. We cannot know. There is no way to audit what was taken. Here's the question. Every engineer watching this has asked themselves at some point. We've known about this class of bug since the 1970s. Why is it still the most common category of exploitable vulnerability in production systems in 2026? And the reason this question is more urgent in 2026 than it was in 2014, AI-powered fuzzing and automated exploit generation. Tools that used to require nation-state budgets now run on a laptop. The asymmetry has flipped. Finding buffer overflows is now cheaper than fixing them. 3 reasons, in order of weight. First, C and C++ are not going anywhere. They run operating systems, kernels, databases, browsers, embedded systems, network stacks. There are hundreds of millions of lines of critical C in production. Rewriting it is not economically possible in any reasonable time frame. Second, the economic incentive has always been misaligned. The people who maintain memory unsafe code are not the people who pay for the breaches. OpenSSL had a $2,000 budget because no individual bank or government felt responsible for the library they all depended on. Third, the alternative languages are only now mature enough. Rust reached production ready in 2015. It is being adopted in the Linux kernel, as of 2024. Microsoft is rewriting core Windows components. Google is migrating Android, but the pace is measured in decades, not quarters. What Rust actually solves, at the language level, is this. The compiler refuses to produce a binary that can overflow a buffer. Not a runtime check, a compile time proof. The class of bug we've been tracing through this video, Missingno, Morris, Code Red, Heartbleed, is eliminated by construction, not by vigilance. This is the real story. Not that programmers keep making the same mistake, that the tools keep letting them. We are slowly replacing the tools. If you ship code, 3 things to take from this. 1. The languages you choose are not neutral. Memory-unsafe languages carry a specific, quantifiable risk, and it's not a hypothetical. It's the bug history you just watched. Know what you're accepting when you pick the tool. 2. Code archaeology is now a tractable skill. AI can read, explain, and audit any code base ever written. The Heartbleed commit, the Morris Worms gets call, every CVE in the database, all of it is now machine readable. But the flip side is real. Attackers have the same tools. The race between automated exploit discovery and automated patching is the defining security challenge of the AI era. And right now, discovery is winning. 3. Infrastructure funding is a design decision. OpenSSL's budget was a foreseeable outcome of how the industry organizes itself. The next Heartbleed already exists in a library none of us are paying to maintain. That's a systems problem. And systems problems have structural solutions. If you want the architect's lens on more of these historical bugs, make sure to subscribe. Stay curious. Keep building.